Nuclear detonation safety began with the first 2 atomic bombs in the summer of 1945, the days of Fat Man and Little Boy.
On Tinian, Northfield, there were 4 great parallel runways. They ran nearly across the total width of the island at that point. Oftentimes, there were accidents such that you could see burning B-29s in the vicinity of the runways.
The Little Boy and the Nagasaki were not safe if we'd had an accident. If it dropped them, or if we'd crashed on takeoff from on Tinian, we would have wiped out part of the 20th Air Force. We'd have lost 400 B-29s and a lot of people. They were not safe. Well, the Nagasaki bomb, which was an implosion bomb, was built up by hand, and the plutonium core was inside the high explosive.
The bomb contained enough plutonium and was sufficiently close to being critical all by itself that there probably would have been some nuclear yield.
Little Boy, the enriched uranium gun-type device, and Fat Man, the more complex plutonium implosion system, posed serious nuclear safety challenges.
So one of the problems, of course, was to make weapons safe, and the only way we could do it was keep the fissile material separate from the assembly mechanism. Now, we didn't do that for Nagasaki. We just took off and hoped everything would be all right.
Both bombs were fully loaded with fissile material at takeoff. Nuclear safety consisted of a system of green and red plugs.
The principal safety measure in a loaded bomb, a bomb that was aboard the aircraft, was electrical safety.
The plugs essentially kept the circuits open from the power supply to the high explosive and its detonators.
In flight, before the bomber was pressurized at 8,000 feet, we took out green plugs and installed red plugs.
And with the arming plugs in, that connection was made. So there was that physical action that had to be taken aboard the aircraft before the bomb was released.
Wartime 1945 drove many hard decisions, including the first use of 2 atomic bombs on Japan, one untested and both unsafe in an accident.
From 1947 on through 1950, the Mark III bomb was the primary operational weapon. And this was a militarized version of a Fat Man.
It wasn't a bomb, it was a collection of parts that had to be assembled by a specially trained team.
And so all the problems that existed with the weapon delivered over Nagasaki also existed with the Mark III.
Meaning if some accident happened to it, you would have a nuclear yield. So one of the design criteria for the Mark IV and all later weapons was that the nuclear capsule would be separate.
The Mark IV was the first weapon to include a function we called in-flight insertion, which meant that the nuclear material in the form of a capsule could be moved along a track and put into the center of the weapon while it was on the way to the target.
The next stage was, instead of doing that manually, was to build within the weapon itself a mechanism that would have the capsule external to the explosive.
So Sandia developed an in-flight insertion mechanism, which the pilot could turn on a switch and the mechanism would insert the capsule inside of the high explosive assembly. The back end of the capsule, of course, had that piece of high explosive which made up the totality of the sphere.
The initial generation of nuclear weapons were capsule-type weapons. A separable nuclear capsule served the interests of absolute nuclear safety, and for a short time, it also provided the means of civilian control.
And in the very early days, civilian control of nuclear weapons meant civilian custody.
And when they had an exercise, the sirens would go off, and the gate between the two fields, so to speak, with the military on one side and the atomic energy and the fissile material on the other side, gate would be open, and there would be a transfer of material with receipts being signed.
Over time, though, that arrangement proved unworkable. The military argued that in a crisis, this would delay a nuclear response when hours might matter. In 1950, this problem came to a head.
The United Nations sent an army to Korea under a single command to hold the aggressors at bay. It was almost
Truman was petitioned by the Air Force of first the bombs and later the capsules for potential use in the Korean conflict.
As the war in Korea escalated and threatened to develop into a global conflict, President Truman approved the transfer of nuclear components to the U.S. Air Force based in Britain.
From the perspective of the Air Force, they did not enjoy the notion of not being allowed to deliver a nuclear weapon in time of war without the approval of this upstart civilian agency.
The idea that nuclear weapons were actually going to be part of, integrated into American security, created a tremendous tension between this idea of civilian control and the ability of the military to plan for nuclear strikes. Withholding authority from the military was ludicrous to a commander like Curtis LeMay.
There was tremendous pressure on the nuclear command and control system to shift from an never-oriented system to something that would be better able to respond in a crisis. And from that time on, the military had custody of nuclear weapons.
There was this romance, if I may use that expression, about nuclear weapons. It meant that the services, if they were to be relevant, which means getting funding from the administration and the Congress, had to be part of the charmed circle of nuclear capabilities. So the Army strove to acquire nuclear weapons. The Navy, in order to demonstrate its relevance in the period, equipped its carriers with nuclear weapons. And of course, the Air Force during that period was central to the buildup.
So every offensive capability they had to become nuclear. Everyone had to have one.
Now what happened in the early 50s, the specter of guided missiles entered the picture. And getting the missile to the target was a Department of Defense responsibility.
Department of Defense for missiles and rockets was responsible for the arming signals, the safety to be provided outside of that nuclear warhead, and the fusing signals to tell it when to fire.
A 1953 agreement carved out areas of responsibility between the DoD and the AEC.
We ended up having to very specifically define where the interfaces were between the AEC hardware and the DoD-supplied hardware.
The interface literally was a connector through which the signals passed to initiate the arming sequence in the warhead.
Sandia was becoming very concerned about supplying a warhead that just required an electrical input to detonate.
We're talking about delivering, let me call them, bare warheads to the services.
A bare warhead would be vulnerable to any stray or intentional voltages. And on the right pair of pins,
it could cause the weapon to go off.
A massive nuclear weapons complex had taken shape in less than a decade, supported by an unbridled enthusiasm for all things nuclear. The 1953 Missile and Rockets Agreement was an addendum to a larger document spelling out AEC and DoD responsibilities for the complete life cycle of nuclear bombs and warheads. Soon, designers and engineers throughout the complex would discover and address the safety implications of this new generation of weapon systems.
Fall 1950. A fierce international war rips through a small country on the North Yellow Sea called Korea. Russia has successfully detonated an atomic bomb. We need to develop and produce a greater number and variety, and possibly even more powerful atomic weapons. Weapons tailored for specialized uses and targets.
The services wanted a nuclear weapon for every conceivable purpose.
In a report to the Joint Committee on Atomic Energy, tactical nuclear weapons represented the future. They promised a revolution in land war. They were the natural answer to the armed hordes of the Soviet Union, and their coming would immeasurably strengthen Western Europe's will to resist.
In the 1950s, we saw weapons added at the rate of about 3 different types per year. The growth was dictated largely by the capacity of the plants.
This is the mile-high city of Los Alamos, the atomic city. This is a modern pueblo created by the people of the United States as a research and development center for atomic weapons.
Nuclear weapons were the product of a demonstration of a brand new capability by Los Alamos and the adoption of that by the military planners.
And whatever we could do, they liked. Didn't matter what we suggested, they liked it. They were very good customers.
The early weapons were maintenance intensive and required preparation time.
The Mark VII used perhaps 20 different complicated testers. We at Sandia felt that these procedures were causing more damage to the weapon than they were finding.
In 1952, the Mark VII bomb was one of the first fighter-delivered nuclear weapons. But by the late 1950s, the Air Force adopted a strike-ready posture, and capsule-type weapons were deemed inconsistent with this new operational readiness.
What they were giving to the military in terms of hardware was burdensome.
Hidden under this security cover is the most destructive force ever devised by man, an atomic bomb.
Well, clearly the idea of having the military having to assemble a bomb didn't at all work with the 5-minute alert concept.
And that was the driver, one of the drivers for wooden bombs.
In 1954, weapon designers envisioned a nuclear bomb that would provide operational simplicity or woodenness, in which the required operational, maintenance, and safety care approaches that of a piece of pine.
The concept was to try to come up with something, a bomb that could withstand years in storage and be instantly available for military use. In the earliest weapons, there was a lead-acid battery used, which took 3 days to prepare. Characteristics of this type made it very difficult for the military to remain on alert.
One of the developments that enabled the wooden bomb was the advent of thermal batteries. These were batteries that were completely inert until torched, if you will, by an electrical signal.
It was a dual-pronged approach. One, go to thermal batteries, become more test independent, and at the same time, I think independently, the physics labs were trying to move towards a physics package design that allowed them to put the nuclear material inside the explosive itself.
Los Alamos' new sealed pit primary was proof tested at Yucca Flats.
Sealed pit technology was a revolution. And it allowed essentially immediate availability.
With the sealed pit, it was a packaged deal, so to speak, and in order for the military to be effective, they had a control of the whole system. We were always worried about what we call accidental nuclear detonation. And when we had the sealed pit, we had to develop at the same time the concept of inherently one-point safe systems.
Duncan McDougall at Los Alamos conceived of this notion that if you ignited the high explosive at a point, it would consume itself.
Meaning that if in an accident the high explosive were detonated at one point, it would not lead to a nuclear event.
The calculations were done mainly by a man named Bob Osborne, and the best we could do and guarantee with certainty was 1 chance in 1 million, that there'd be no yield greater than 4 pounds. And I had based this 4 pounds criteria on the basis that there might be an accident on a ship, and the nuclear radiation from such an event could be contained within one of the compartments on the ship.
The new sealed pit primaries prompted a change in the safety emphasis, from controlling the nuclear material to controlling the electrical energy. In early 1957, there were 14 new weapon systems in the pipeline, all based on Los Alamos' sealed pit design. One of these 14 systems was the W-49, a warhead mated with the earliest intercontinental and intermediate-range ballistic missiles.
The 49 was the first of the warheads intended for reentry vehicles that was small enough to be practical in a reasonable sized missile and still have a large yield. Early on, the Atomic Energy Commission provided the nuclear explosive package and the fire set.
And the Department of Defense was responsible for the fusing system, which would deliver the proper signals to the warhead at the appropriate time to cause them to detonate.
Arming and fusing signals, together with the source of power, were supplied to the warhead by the missile.
To be compatible with DoD systems, you had to have an interface where the two came together, and that was the form of an ordinary connector with pins and sockets. I can remember in the military as a young lieutenant, my favorite tool was a voltmeter because now I could troubleshoot the circuits in a logical way. It was just a simple matter of removing a plastic cap for weather protection and doing these tests.
The concern grew about a friendly fiddler or someone just mistakenly connecting a voltage up and getting a very bad result.
A single individual with information about schematics, which were widely available, and a battery in a lunchbox could detonate a nuclear weapon. This was not good.
The W-49 was not considered to be an especially dangerous system or different than any in the past. It was just the time to begin stepping up to the plate, change the situation that existed in the past of not having some kind of environmental protection in the Sandia AEC hardware.
I took it upon myself to authorize the design modification, if you will, to provide a first-generation environmental sensing device, in this case, an accelerometer.
No longer could you come up to the interface and put signals that would pass on down. It was a positive block until sometime in the deployment to the target,